Oh, well, that's exciting.
I don't have a system.
All right, so there's not a whole bunch of folks here, but I'm going to go ahead and get started with stuff now because there's always the video available for whoever didn't show up. So what I'm planning on doing is I'm going to spend 8-ish or so minutes finishing up what I didn't get to on Monday. So this way it's at the very start of the video for anyone who's curious about that, and you'll have to go poking around. And then I'll take any questions that you guys have, and then after that I'll just start going through the study guide and talking briefly about everything there and then answering any questions that come up as part of that. So hopefully that seems reasonable, and if you're not interested in infrastructure management, at least it will be over soon. So we talked on Monday about microservices and how you can take an application and break it up into a whole bunch of different pieces. But one thing that we haven't covered in a whole bunch of detail so far in this class is how do you actually handle deploying an application, creating something that a user can actually interact with, something that isn't just running on your local development environment. And the way that most web applications are deployed is using something that's known as a 3-tier architecture. And what this usually consists of is you have a web server that handles serving HTML pages, CSS pages, JavaScript, basically everything that gets rendered client-side in the user's browser. And then you have an application server that handles all of your dynamic server-side processing, fulfilling API requests, doing CGI stuff like PHP or whatnot. And then a database server, which unsurprisingly runs your database and stores all of the stuff that you really don't want to end up losing. And this works reasonably well. It's nice because you can split your application up into these different bits and pieces. Each piece has a relatively well-defined role, so it's relatively modular here. And then you can use different pieces of technology for each of these here. But sometimes you want to go beyond this, particularly if you have larger applications that are going to be used by more people, and there's really more things you have to take into consideration here. So the first thing that we introduce here is DNS, and DNS is what's responsible for taking a URL that you give the browser and actually turning it into an IP address that can be resolved. So normal people don't like working directly with IP addresses because memorizing something like 66.57.134.10 instead of google.com is not going to be very friendly. So you use actual URLs, you use host names for stuff, but that's not what the internet actually uses. So DNS turns a request for some domain into an IP address that can actually be located and actually can be resolved here. And if all we're doing is just a basic 3-tier system without any of the other fancy stuff we're about to get to, advanced DNS doesn't really do us a lot of good. But what the advanced DNS does is it actually enables us to have more powerful infrastructure like we're about to see in just a moment. So this way it lets you do things like latency-based routing where you send things to the server that is going to be able to fulfill the request the quickest, or you send it to one that has the lowest load on it, or one that is geographically closer to you or whatnot. And we'll see that in just a moment. But the way this works is that you have a request that comes in, and then from there the DNS resolver figures out the IP address that is actually able to handle. And the first, probably most straightforward application to think about for the DNS applications is load balancing. So we talked a couple weeks ago about performance testing and how we actually care about having a website that is not stupid slow. And one thing that can help make sure that you have a fast web application for people to use is load balancing, where you scale requests out across multiple different hosts that are capable of handling it. And this is helpful because computers are fast, but computers are only so fast. And even if you throw $20,000 at getting a computer, there's still only so many requests you're able to handle. And something like Google or Facebook or Amazon or whatnot is going to have way more requests that come in than a single computer is able to satisfy. So what you can do then is you have within each tier of your application, within the web tier or within the application tier, you have not just one system, but 2 or 3 or 3,000 or however many your budget and your users call for here. And then you have a load balancer here that is responsible for figuring out which of these hosts has the lightest load on it. And then it will either suggest to the user, go use this one, or it will automatically go do it for you. So this is a screenshot from the Tech Power Up application download site. They have a whole bunch of nice utilities and whatnot. But they say, well, there's 2 systems that they have available in the United States. One has a load of 1% on it. One has a load of 2% on it. Okay, well, if one's 1% and the other one's 2%, that's basically a negligible difference at this point. And I did try reloading the page a whole bunch of different times and trying at different points, but I wasn't able to actually get a good image that showed, well, one's at 50% and one's at 1%. But either way, a load balancer can help you pick the system that has the lightest load on it, and then hopefully the one with the lightest load will be able to fulfill your requests quicker. And then in addition to it automatically finding the system that is fulfilling the fewest requests, depending on how you have your infrastructure set up, you can actually have it dynamically spin up extra images that will serve as your applications here. So it might determine, well, we have 2 application servers running right now, and for the past 30 minutes, both of them have been at greater than 80% load. This is probably a bad sign because you're running it close to capacity for an extended period of time. So if you have really nice automation set up, it can then bring up a third one and then drop the load down across all of them. And perhaps it can go and then decommission the third one in some later period when it proves not to be necessary. And there can be various different conditions you use as part of this, like latency time, how long it takes to satisfy a request, or CPU utilization, or how many requests end in errors as opposed to ending in some sort of successful status. So load balancing lets the system automatically pick the host that is capable of servicing the request quickest. The next thing that we can also do with this to have a scalable web application is using a content delivery network, something that is responsible for serving up frequently accessed files or large files. And this is helpful because if you have a whole bunch of static content, that is content that doesn't really change, that is the same for every single user of your website, application servers and really typical web servers are not particularly efficient for serving this up. This is really how most websites behaved back in the late 90s, early 2000s, before there was per-user behavior, different behavior for every different user type, every different user, like you see on Facebook, like you see on iTrust2. But for content that doesn't change much or doesn't change at all, it's not particularly efficient to keep serving it off of the same system, and it enables a very common type of denial of service attack. Basically, the most common type of distributed denial of service attack is to repeatedly request some large content, because this ties up a fair amount of resources on whatever is serving back the website, and then can relatively quickly overload it at not particularly great cost to the attacker. So using a content delivery network lets you offload these big files or other static things like your JavaScript libraries, your CSS files, to some other third party, something like Cloudflare or whatnot, that then has their own intelligent stuff, has things like CAPTCHAs to make sure that you're not a robot before serving it back. So you offload that to someone else, make it their problem, and then they have specialized stuff to make it not very much of a problem. The next thing that is helpful after offloading these big things to a content delivery network is using caches. And caches are something that you're all, at least you've probably heard of at this point. Caching is basically the notion of, well, let's not go recompute or re-retrieve everything expensive every time that it's requested. So you've probably heard of CPU caches when you took operating systems or assembly, where the CPU chooses to store the most commonly accessed stuff, and then virtual memory is used, where you can have some of your data that resides actually in physical memory and some that gets offloaded to disk. But either way, the point is that we want to use smaller, faster storage for stuff that is expensive to retrieve and is retrieved regularly or is expensive to compute. So the data that you care about then gets cached actually in memory and not on disk, so that you don't have to go look it up off of disk every single time. Mechanical disks are becoming less and less common, but even a good quality flash-based solid-state storage device is still a couple orders of magnitude slower than purpose-built physical memory. So you use faster hardware for this, so you don't have to pay the cost of looking it up. Or you cache stuff that is potentially computationally expensive to compute here. So something like the front page of Reddit is something that, at least if you're not signed in, is going to be approximately the same for every single user. But it's not going to be the same every single day or every single hour or something. I don't know how their algorithms work, but I suspect that they recalculate stuff every 5 minutes, every 10 minutes, every 30 minutes or something. But within that 5-minute or 30-minute block, everyone is going to see basically the same thing. So it wouldn't be quite efficient to offload it to a CDN, but you can cache it instead of recomputing. Or something else like finding driving directions from here to Florida or whatnot over spring break. That's something that probably wouldn't be popular, and although there are good algorithms as you learn data structures, good algorithms only get you so far, so maybe they'll also go cache this sort of things here. So this says, let's not spend time recalculating or re-retrieving stuff when there's not really a need for it. The next thing that we can do in terms of creating a scalable deployed copy of our application is using availability zones. And what this says is we basically take the entire thing that we've just set up and then we clone it. And that says, well, maybe we have an earthquake or a tornado or goblins or whatnot that comes and destroys our data center, something that will render, or something that would have normally rendered our application unavailable because our data center is flooded or been attacked with axes or something. So if we create multiple different copies of everything, then we're able to better deal with something bad has happened here. Additionally, one other thing you can do with this is it makes it much easier to deploy new versions of the application. And the way that this works basically is you have one copy of your application, the old version that you know works, running in one of your availability zones. Then you deploy the new copy that you're hoping works to the other copy of your availability zone. And then you have your router here start sending requests over from the old one to the new one. So maybe originally 100% of the requests were sent over to the old copy of the application. Then you send 1% over to the new one, then 5%, then 10%, then 50%. And then once you're reasonably confident that it's not going to explode, then you can send over 100% of the requests. Make sure that it still doesn't explode, and then after that, you can go upgrade the previous copy of things as well. So this makes upgrades relatively seamless to do because you don't have to take down the entire application, and there's not going to be some awkward period of 30 minutes or 5 hours when everything's offline because you're upgrading your application servers. The next thing that we can do that helps here is geographically distributing our application across the world. So when my dad talked about performance testing stuff, he said, well, it's relatively quick to make a request to a system in Cary, relatively quick to make a request to a system even in New York, but it's not particularly quick to make a request to a system in Mumbai or Shanghai or Moscow or something. So what you do here is that you have copies of your environment, and you have, again, basically the complete environment here that you then package up and scatter all over the place. Maybe not all over the place. It doesn't really make sense to put one in Antarctica just for the penguins, but you can have ones scattered across highly populated, geographically disparate parts of the world. So if you're familiar at all with Steam, if you've used Valve's services there, you've probably seen that they have game servers that are located on the U.S. East Coast, I believe in Virginia, some that are located on the U.S. West Coast, maybe Los Angeles. There's others in, I believe, Belgium, some in Romania perhaps, and then various different locations out in East and Central Asia as well. So you geographically distribute your application so that regardless of where a user is, they're going to have a decent experience because every single request doesn't have to go to the opposite side of the world here. Additionally, an advantage of this is that by scattering your application out around the world, you can have what are not just actually identical copies of your application, but very similar ones. So different regions have different rules for how data has to be transferred, and different governments have different expectations for basically what they're going to demand from companies or from organizations. So Europe has what is probably the most user-friendly privacy regulations, in that users are told explicitly this is what is going to happen, and there's relatively less that governments are able to access and that companies are able to do without your consent. I would expect China, on the other hand, the government is able to access pretty much whatever they want. Certainly the American government seems to believe similarly. So European citizens might feel happier having their data stored on European servers where the NSA or the People's Liberation Army aren't going to have access to it, whereas the Chinese might insist any of our data is going to be stored somewhere in our country. So you split up your application into different regions, and it gives better user experiences and makes it easier to comply with local regulations. There's other stuff here that is helpful as well, things that you can do to help make sure that your application is running all right, that things aren't falling apart. So monitoring gives you a way to check on the status of things, see how many requests are coming in, to see how quickly the requests are being serviced, see if there's anything that's been sitting for a long time. Basically a health check of your application to see if there's no imminent issues. Client messaging is a way to actually just send out messages to people when need be, like you've seen with iTrust2 and its email stuff. The email stuff in iTrust2 is not great. There are better ways of doing this. That also falls into the email services there. And then indexing can help you retrieve your data more rapidly, basically by having indices the way you index and your data structure, rather than having to search for everything every single time. So how do you actually do this once you care about all of these things? Well, OpenStack is an open source way for deploying cloud-based web applications. Like most open source projects, the documentation is horrendous, but it is out there. It is something you can use. VCL, the Virtual Computing Lab, is something I'm sure you're all familiar with. We have. It's based off of an Apache project, I believe. So again, you can also go set that up if you feel so inclined. And then pretty much every big name within the computing industry has their own cloud computing platform as well. Amazon, of course, does. Microsoft does. Google does. Oracle does. Cisco does. IBM does. It's basically just a question of who's offering the services that you specifically want at a price that you want, and then which company your organization has a history of doing business with. So there's a whole bunch of ways of doing this. If you're curious about this, Dr. Parnan here in the software engineering department teaches, I believe, CSC 419 now. It was originally a 500 level course and then became a special topics course, and now it's a regularly offered one that is on DevOps and modern software engineering principles. So DevOps includes stuff like how do we automate a whole bunch of stuff? How do we automate our tests? How do we automate our infrastructure? What does this infrastructure look like? I took the 500 level version of this course and found it quite interesting. So if this was neat, he's offering that. Martin Fowler is a big name in software engineering, and he has an article up on microservices and what he perceives to be the pros and cons, like we discussed on Monday. The stuff on infrastructure management, I don't have a site for that, since that mostly came from Dr. Parnan's course materials. But those are our links and a class to look at if you're curious about it. So that is what I have, what I had to cover still from Monday's class. If there's any questions now, I would be delighted to answer them. Just tell me anything, or I'll start talking about stuff, and if questions come up while I'm talking, then interrupt to ask whenever you feel like. But I'm going to take a moment or two to get the study guide pulled up so I can start going over that, and you can think about what questions you have while I'm doing so. Yeah.
Is that DevOps course going to Docker and Kubernetes kind of stuff?
So it did a bit, at least in the graduate one I had. We did not do a lot on that. We mostly covered things like how do you use Ansible to automate deploying everything you need on a server, or setting up your Jenkins environment or whatnot. But yes, I believe we had a day on container-based stuff. All right. So All right. Well, if there are any other questions, I'm happy to answer them now. Otherwise, I obviously have the study guide up here. So I'll just start talking about stuff. Interrupt me whenever you feel like. I can talk to an empty room whenever I feel like talking to or actually answering questions is more interesting. So as for the parameters of the exam itself, it is pretty much what Dr. Heckman said yesterday. Final exam is a week from Monday, 8 a.m. I know that's far too early. I'm sorry. We don't get to choose. The final exam will be similar in format to the midterm exam. So there will be some multiple choice stuff, some short answer stuff, some longer answer stuff. And hopefully you won't be particularly time constrained because it's 3 hours and we really don't anticipate for you to take 3 hours. So if everyone was taking a 3-hour exam, that would be an extraordinary amount of grading for us to do, and there's already 130 exams to do. So similar in content, similar in style to the midterm exam, cumulative. So it will be focused primarily on, or a majority of stuff is going to be stuff that you've seen since the midterm, but not exclusively that. Obviously, you have to work by yourself. You're not allowed to use a computer. Don't do stupid stuff. It's the same constraints you've seen through pretty much the entirety of the computer science curriculum. So that is the parameters thereof. As for content, I can just start talking about stuff from the top and going through it at this point. Yeah, doesn't look like there's any questions. So I'll talk about stuff. So you should be familiar with the different course technologies that we have used at a high level. So aside from Java, it is fair game that we might ask you to write some Java code. We're not going to ask you to write code that uses specific Hibernate annotations or specific Spring stuff or specific Selenium stuff. But you should be familiar with what do each of the technologies do, what do you use them for, and what sort of problems do they solve. So GitHub, of course, is helpful because it's a way to keep track of all of your code. It's a way so that you can migrate your stuff between different computers. It's or so you can work on your project on different computers. It's a way for multiple people to collaborate on a project. GitHub has good and increasingly better teaming stuff, like pull requests and issues, which have been there for a while, but now there's the GitHub projects for keeping track of this needs to be done during this phase of the project, and so on and so forth. So that's why that's useful. Jenkins is nice as our continuous integration environment, so every time a commit comes in, or every time you tell it to, it will go compile a copy of your project, run all of your tests, do some other post-build stuff if you feel like it, and then prepare a nice, pretty report of this is what we've done and this is where things stand. So this way you don't have to run everything on your local computer all the time, and an entire team can see where a project stands. And you can even have notifications to a Slack channel or a Discord channel of, we had this commit happen, or this commit was made, we built the project, this was the status of it, and if something goes wrong, you can go actually tag whoever appears to have broken things, like, now you have to go fix this. Maven is nice because it lets you organize your project and organize all of the dependencies for it, because otherwise defining how you build a project is annoying and managing all of the Java dependencies is worse. I have only had the misfortune once of working on a large project that was not Maven-based and where we had to deal with all of the jar files independently, and once was enough to convince me never again. So Eclipse and most other IDEs have straightforward ways to create Maven projects, and then it manages your dependencies largely automatically for you. REST APIs are nice because it lets you have different parts of your systems communicate using some well-defined interface, some well-defined format. You say, I expect requests to come in, these type of requests, this type of data to be provided. In exchange, I will give you this other type of response according to these constraints that have been laid out. In our case, we use it for communicating between the front-end stuff in JavaScript and the back-end stuff that's in Java. But like we discussed with microservices on Monday, you can use it to communicate between whatever you feel like. Hibernate is nice. It is a object relational mapper, which lets you go back and forth between Java objects that you work with in memory in your Java world and database tables that exist that get persisted outside the lifetime of your program. It's nice because the alternative largely is using Java's SQL API, which actually is not particularly bad. I used it in the databases course, and it's not bad to work with writing SQL queries and extracting stuff out of it. But it's certainly more tedious than it needs to be. So this generates the SQL for you automatically and makes it straightforward to save objects to the database, retrieve them from the database, and not have to write your own SQL code for it. Spring is magic glue that makes the web application, the Java application stuff work properly. So Jetty is what actually serves as our Java application server, like we saw as the middle tier in our 3-tier architecture a moment ago. But Spring is what lets you write basically normal Java code like you've been working with for several years, and then have it actually turn into a web application. There are various different frameworks for doing this with. You may have worked with JSPs before. If so, my condolences. But Spring gives you a pretty straightforward way to write largely normal Java code and then get a web application at the other side. Selenium, love it or hate it, is a way to automate web browsers. So it lets you, rather than sitting down at your computer and doing a whole bunch of stuff by hand of, well, I want to scroll here, I want to go to this tab, I want to go search for something else, it lets you define, here's how you're going to go run through everything. It makes automated testing of web applications much more straightforward, because otherwise you don't really have a good way to automate it. You don't really have a good way to do automated testing of this. One of the internships I worked at, I was doing web development. We didn't have any automated front-end tests for our application. We had one woman, bless her heart, who did acceptance testing on every single application that we produced. It was an extraordinary amount of work, and I don't know how she managed to cover so many different things, but Selenium helps make that less painful. Cucumber is nice-ish for writing behavior-driven development tests, because it lets you separate out, this is what I want the test to do, from this is how the test is actually working. So the feature file is something that you can come up with early on in the life cycle of your project, because it isn't really bound to any specific implementation. And it is additionally sufficiently non-technical, you can show it to pretty much anyone and they'll be able to read it. And be able to say, yes, this seems reasonable, or no, it looks like you're missing something here. And then you separately write the step defs that actually carry out the logic behind it. So those are the technologies we're using. Hopefully all of those descriptions didn't come as a surprise, because at this point you've been using all of these technologies all semester. But if you have follow-up questions, I would, of course, be happy to answer. All right. The next topic that we have here, and one that is relatively newish for this course, is requirements. So how do we get from a customer says, I want this thing, to something that software engineers can actually implement, something that is nice and precise? So to this day, of all of the courses I've taken here, the requirements that Dr. Sturgill gives in his CSC 230 course are probably my favorite requirements that I've ever worked with, because he specifies in extraordinary detail, this is exactly what is expected, this is what you will do, this is how you're going to handle this type of input, this is errors that are expected, and he even provides some idea of how you're expected to break down the application. And this is a way that requirements were very often done back in the 1980s and the early 90s, is having these very well-specified requirements. And there were times I wish I could have been a software engineer in the 80s, because I really do love this. But it is rarely the case that customers give you something that is as detailed, as well elaborated, as non-contradictory as Dr. Sturgill gives us. So instead we have to take requirements that we get from the customer and figure out what is it that we can do with these. So the first thing, how do we start identifying what classes we're going to need from a requirement statement? Well, for the most part here, we're working with object-oriented programming, so it is classes we care about. And typically you can turn nouns that are present in a problem statement into classes that are going to exist in the system. And then after that, you have a whole bunch of classes, and then you start to figure out, well, what inheritance structure are we going to use? What composition structure are we going to use? Maybe you think of, well, we had nouns in our system for a patient, nouns in our system for an admin. We're going to create those as different types, but then, well, what do they have in common? Admins and patients are both users. They both ought to be able to log into the system and do X, Y, and Z. So then you think of the inheritance relationship between user and then subclassing it to admin and patient and so on. So think of the nouns, that becomes your classes, and then you can start actually composing it together after that when you're doing your actual design later on. What or who are typical stakeholders for a system? The stakeholders really is anyone who has something to lose if the project fails. I think that's a straightforward way of thinking about it, but this is going to be the customer that you're ultimately developing the application for. It's going to be, of course, the developers themselves who are working on the application. It's going to be anyone who helps support the developers through this, like testers, like project management folks. Those are increasingly less separate roles as developers are expected to handle more and more of this themselves. In addition to just the customer who is actually paying you for the project, there's also, though, going to be the users, whoever this customer wants the project for. So I read an article not too long ago about different learning management systems, Moodle, Blackboard, and whatnot. And apparently a whole bunch of people have been leaving Blackboard because it's terrible. And the customer, or some executive at Blackboard said, we don't know why we're losing all of these. We don't know why we're losing these customers. We have the most features. It's like, well, yes, you might have the most features, and this looks great when you have an itemized list of all who has the most features. But when the features are there in a way that no one can figure out how to access them, or it's down 12 different button clicks or whatnot, it doesn't really matter. So you have to deliver something that not only the folks who are paying you are happy with, but ideally the folks who are paying them or are otherwise users of the application. So we want to develop our applications taking this into consideration. What are functional versus non-functional requirements? What are constraints? What type of requirements are security requirements? And then identify them as each. Functional requirements typically say something like, when I do X, then Y should happen. It specifies how the system should function and what it should do or what it should not do. When I enter in my password incorrectly 10 times in a row, I should be locked out for 5 minutes or 10 minutes or whatnot. Or when I click on the document, or when I document an office visit that has these different things that are filled in and click the submit button, then it should be documented and the information is saved and presented back to the user. Non-functional requirements are things that are sort of implicitly properties of the system, and this is often used as a way to specify performance requirements or whatnot. So non-functional requirements don't describe something the user does, but describe how the system behaves regardless. So something like 95% of requests should be satisfied in 1.5 seconds or less. That's not really a functional requirement because it's not a single flow through the application you can go test through, but it's an inherent property of the system we would like to have met. Constraints are used to specify things like what technology stack are we going to use, what platform does it need to be able to run on, what devices do we care about, because there's obviously very different concerns when you're developing an Android application versus a desktop Windows application. Surprise, surprise, but how the user is using your application is going to impact a great deal of what you do. Windows 10, for instance, is something that Microsoft has clearly designed with tablets and touchscreens being the foremost of their concern, and it shows. It's a great touchscreen operating system, questionable for a desktop still. So the constraints of what you're running on will very much influence what you do here. What type of requirements are security requirements? This was a question that we had on the midterm exam, I believe. And the best way to do security requirements is to express them as functional requirements. And the reason is functional requirements are by far the easiest requirements to test. Functional requirements specify when X happens, then Y should happen. When Y happens, Z should happen. And then you can very quickly get a yes or no answer of did X lead to Y, did Y lead to Z, or not. So if you can express your functional requirements, if you can express your security requirements as a functional requirement, then it's easy to test. Well, I tried to log in with incorrect password 5 times in a row. Did I get locked out? Or I tried to access an admin page when I was logged in as a patient. Did I get to access the page or not? So these are the easiest to test. Security is an important part of our system, so doing our security requirements like so is helpful. Identifying requirements as each of these types is something that's sort of hard for me to talk through here, but given what we've just said about what each type of requirement is, hopefully given a specific requirement, you're able to classify it. Creating acceptance scenarios for a functional requirement. This is basically, you take a functional requirement and then you come up with a concrete instantiation thereof. So just like what you've seen with object-oriented and class-based programming, a class basically is a template that you can create concrete objects out of. A user might have a username, they might have an address, they might have a password. But a user in the abstract sense has none of these. A specific user might have the username Joe, they might have the address that is 890 Oval Drive, and they might have a password that is root1234. So you instantiate the user class and get a user object that actually has things filled out. Acceptance scenarios have a similar feel of you turn a description of what the system should do into an actual acceptance scenario where you fill out real values and see and then specify what is supposed to happen there, and then you can test, does it satisfy this or not. Compare user stories and use cases, including format and content. All right. Use cases are what you guys have seen the most at this point, and is what Dr. Heckman is most fond of and what I think I'm most fond of as well. Use cases have a relatively rigorous structure that specifies preconditions that must be satisfied, a main flow that describes at a high level what are we doing here, subflows that are any supporting flows or different ways that you can interact with this, alternative or error flows that say these are bad things that might happen and here's what we're going to do with it. Because we're working specifically on a medical record system, here we also have logging that says this is what we're going to keep track of. And then there's usually going to be data format and acceptance scenarios. Data format says something like, well, we care about we care about what the calendar format we're going to use is, or is this thing allowed to be an integer number? If it is an integer number, between what values, or is it going to be a floating point number? And then acceptance scenarios are, like said, concrete instantiations of the requirements here to test does it work or not. So that is typically how we write use cases. User stories are more analogous to individual flows through a piece of functionality as seen by a specific user. So a use case will describe this is a large piece of functionality. User stories will say something like, as a user of XYZ type, I want to be able to go do ABC thing, and then the system will do DEF or whatnot. So as this type of user, I want to do this thing, and then the system will do this other thing here. So user stories then are usually written in more casual language and usually express less than a use case does, but you can often combine together multiple different user stories to make up a single use case here. And then a scenario is part of a use case. It describes a specific path that is through it. What are the criteria for requirements validation? This is basically making sure, do we have requirements that are concise, consistent, complete, and so on. We have the full list in the the requirements course slides, but it's making sure that the requirements that you have written faithfully represent what the customer said that they wanted. You're actually implementing you're actually going to implement what they have told you. You also want it to be complete, so not only does it do what they want, but does it do everything that they want, that you don't have some piece of functionality that is going to get missed here. You prefer concise because given multiple ways to say the same thing, you can either have a complicated, verbose way of saying it, or you can have a shorter way. The shorter way is almost always better because then there's less ambiguity, less chance for getting confused, and so on. And then, of course, you want requirements that are going to be consistent, because if you have requirements that are inconsistent, as in one says to do one thing, another one says to do not that thing, it's very difficult to actually understand what it is you're supposed to be implementing. So you want to make sure that the requirements tell you one thing and really only that one thing to do, so that there isn't the doubt of what approach do we take here. Then finally, what is the difference between requirements analysis and requirements modeling? And the difference here really is that requirements analysis is about coming up with requirements that make sense to a customer, and requirements modeling is about coming up with requirements that make sense to a developer here. So requirements analysis is basically just gathering information of the customer says they want all of these different things, and then you start to compile it together and make sure that, yes, they agree that these are all of the things that they want. And then requirements modeling is you take these things that the users say they want and that they're happy with, and then you're able to turn them into use cases or turn them into user stories or the like here. So starting to move beyond, I would like this, or the user should be able to this, and then coming up with more precise use cases that really do give developers a precise thing to design from and then implement from. Any questions about any of the stuff I've just talked about for requirements? You're all good? Clear as mud? Great. Well, in that case, I'm going to take 30 seconds to get a drink, and I'll be back then and talk about software design. All right, so the next thing that we have is software design, and software design is quite fun because it's how do we go from this is what the user wants to something that we can actually implement. So I believe that we have a quote from Professor Lasher about how months of programming can save you hours of design time, and that is perhaps exaggerated to an extent, but at the same time, you wouldn't build a house without designing what it is you're going to do. And you hopefully wouldn't build a software system without designing what it is you're going to do. Because, yes, this might work all right for a really tiny application, just like it would probably work okay if you're building a doghouse or something. If you're building any reasonably large system that you're probably going to be working with professionally, it is going to be complicated. There are going to be trade-offs. There are going to be things that you have to think about. And if you just jump straight headfirst into the implementation, you're going to land on your head and it's going to hurt. So we design what we want, and then we can make sure the design makes sense, and then we can go actually do the implementation after that. So software architecture is at a quite high level. What does our application look like? What paradigms are we following? And what high-level things are we using to guide us here? So we have information in the architecture slides I'll pull up to briefly talk about the main different architecture patterns here. But architecture is sort of the 10,000-foot view of what it is that we are working with here. So the four main architecture patterns that we covered here is the data-centered pattern here, where we focus predominantly on what is the data that we're working with and how are we going to store it and how are we going to enable the users to interact with this data here. And we discussed the repository approach to this, where your data is stored largely in a pretty well-defined format here, and users largely just retrieve data from the system and then consume it and upload it in well-structured formats. Something like YouTube or whatnot, where it serves as a repository of videos that users can search through and access and sure upload their own ones, but there's not going to be particularly chaotic interactions with the data that is stored here. The Blackboard approach, I think that if you're going to summarize it in one word, it is chaotic, because here you have data that is in a substantially more chaotic. It is a substantially more chaotic way of storing data, and what each person who's interacting with the data does depends on the state that the data is in, and then they go manipulate the data, and then everyone else starts paying attention to that and maybe does something. Implementing a good Blackboard system is it's something I've actually never done, but it's something I would expect to be quite difficult to do, because there is, how do we keep track of all of this, and how do we keep track of when each of the observers of our data or our knowledge sources here needs to actually go do something to it. The second of the four big architecture patterns here is the call and return approach here. And this describes basically if we have one main execution through our program that calls something and then that returns, and you could call something else and that returns, and so on and so forth. So the first approach here that we have seen is the main program and subprogram paradigm, which is basically how C works. C has a main method, and main calls A calls B returns, A calls C returns, and so on. So you have things that call each other in return in a relatively orderly fashion. We're going to pretend for now that set jump and long jump don't exist because they're horrendous, because then it violates this approach. But otherwise, these patterns or these programs are typically straightforward to reason about, because you can trace the flow of control from one thing to another thing and back and so on, and see what's happening. Object-oriented programming is of course what we have done in Java, what we do a bit in 1.16, we do a whole bunch more of in 2.16, what we've done here. Object-oriented programming is all about decomposing the things we care about into objects, coming up with meaningful relationships between the objects, and then using dynamic dispatch to say, well, we don't care at compile time exactly what concrete implementation we'll have here, but as long as it is a subclass of this type, then things will just work. The layered approach also falls into this. The layered approach you've probably seen if you've taken networking. You certainly saw it if you took my operating systems course. You probably saw it if you took any of the other ones. Here you can decompose your system into layers, impose pretty strict interfaces between the layers, and then say layer 1 provides an interface that layer 2 can use, 2 provides an interface that 3 can use, and then you can build things out in layers like that. The advantage of this is that if you have your interfaces that are well defined and you actually adhere to your interface properly, you can switch out my layer 2 for your layer 2 or your layer 2, and it doesn't matter. It makes it nice and modular. The downside is that not all problems lend themselves nicely to being decomposed into these layers. And if layer 2 needs to communicate with something in layer 5 or the other way around, it's non-trivial to do that. The third of our main architecture patterns here is data flow, and this describes, unsurprisingly, how the data is going to flow through your system. So you start here with some data that is to be processed, and then you do something with it, and then you do something else with it, and then you do something else with it. And then hopefully at the other side you have something that resembles what you want. So as examples of this, we have the batch sequential approach, which basically says, I'm going to take all of the data and run it through this first transformation, and then run it through the second transformation, and then run it through its third transformation, and so on. So an example of this you're probably most familiar with is if you've worked with the Unix command line at all. You've probably used the pipe operator, the vertical bar, to pass one thing, the output of one thing into the input of another thing, and then the output of that into the input of another. So you keep taking your data, you run it through through a bunch of different transformations here, and then you keep sending it on to the next one after that. And that is basically what the pipe and filter approach does here as well. So if we hop down a whole bunch here. All right. So batch sequential is a type of pipe and filter where there's no streaming here. Pipe and filter in its pure sense the pure sense of pipe and filter can have all of the different filters running at the same time. So you can process a little bit of data through filter 1, send its output on to filter 2. 1 keeps working on more data from the user while 2 uses the output of 1, and then you keep sending things down a little bit at a time. So a physical real-world example of this is assembly lines. Assembly lines are used to build products, of course. You typically have a whole bunch of different people that are working at every single step of the assembly line at a time. The first step of the assembly line builds one thing, they pass it down to the second step. The first guys keep building that same one thing while the second guys use what the first guys just built, and then you keep moving things down one phase at a time. There are some types of data, some types of problems where this doesn't work as nicely with, and that is where we have our batch sequential, which is this degenerate form of pipe and filter where there is no streaming, and you have to finish one phase before you finish the next phase. Because sometimes the output of one phase is going to depend on having the full picture, having all of the data available. And if you don't have all that data available, then it is sort of by definition meaningless right here. And then the final of our 4 main architecture patterns we have right here is the event systems group. And this describes how do we respond in reaction to something happening here. So implicit invocation uses things like having functions that are passed in as arguments to other functions, things that get implicitly invoked when things happen. Explicit invocation largely uses things like button presses or the user explicitly saying, go do this thing, and the system goes and does that thing right there. And like I believe I mentioned when we covered architecture earlier in the semester, it is possible to combine multiple of these different patterns together right here. So as an example from our senior design project that I believe I showed you before, we used a batch sequential approach here for processing data, but we also used object-oriented programming. So we wrote it in Java, which is, of course, an OO language. And we did do different things at different stages here using dynamic dispatch based on exactly the data we were working with. But it was this batch sequential approach. If we do one thing, and then we do another thing, and then we do another thing, and then so on and so forth. So you're not limited to just one architecture pattern. You can combine multiple different ones together as seems reasonable for the problem you're solving.
For event systems?
Sure.
Is that triggers on page
load? Right. So there's a whole bunch of different things that can trigger these. So on page load is fine, or on a button being clicked, or you can have timers that say after 3 seconds go do this, or a network packet comes in.
Is on page load, you can say that implicit?
Yeah, I would say that's an implicit one because you aren't explicitly having the user say, go do this thing. It just implicitly happens whenever the previous thing, namely the page load, finishes. Make sense? Okay. All right. So those are the big architecture patterns that we have looked at, and a brief description of each one. What are the 3 parts of a class's representation in a UML class diagram? This is something you are probably familiar with from 216 at this point because you did an awful lot of UML diagrams there. But you have the name of the class, you have the fields or variables that exist on the class, and then you have the methods that exist on the class. And the only part of this that is actually mandatory for the UML diagram is the name of the class itself. And the reason for this is there are reasonable situations where you might have either methods but no fields or fields but no methods. I struggle to imagine a scenario where you would have a class that has no fields and no methods in it, because at this point, what are you doing? But you might have utility classes that contain nothing but static methods and then no fields in them. Or you might have data classes that contain nothing but fields and then negligible methods, just getters and setters, or I don't know, if you felt like it, make everything public. Don't do that. Don't make everything public. But either way, you could have a class that has one or the other, but not both. You could have one that doesn't have either, but that seems silly. Be able to show the different types of relationships in the UML class diagram: generalization, association, aggregation, composition. Frankly, the best resource for this, I believe, is Wikipedia. Wikipedia has a pretty good source on making class diagrams. Thank you. I'm not going to start drawing class diagrams up here showing these different types of relationships because I will get it wrong. I don't really draw class diagrams with any regularity, so I don't have the syntax memorized, but Wikipedia does a pretty good job with this, showing at a high level what the different arrows and lines look like. All right. How are scenarios used when drawing sequence diagrams? Probably a necessary prerequisite for this is, what is a sequence diagram? Well, a sequence diagram is, as you hopefully remember from working on the last project, a way to do dynamic design for the back end of a system. A sequence diagram shows these are the different bits and pieces of our system and how control flow is passed between them and how basically conditional logic happens and then returning something to the user at the end. And a sequence diagram typically represents just a single scenario or single acceptance scenario. So you have a sequence diagram that shows, I have this thing happening, and then this is what is going to happen here. The user makes a post request to the office visit endpoint with some data that corresponds to an office visit. Then the API office visit controller is going to go create an office visit based off of the form, go set a whole bunch of stuff, try to save it to the database, or use the domain object, save it to the database. It will either save, in which case we then log that this has happened and return a success message to the user, or it doesn't save, in which case maybe we log that something bad happened and return an error message. But you show up at the top the different entities of the API controller, the office visit class, domain object, the database, and so on. Time flows from top to bottom, and then you have arrows that go left to right to show method calls and right to left to show that you've returned from the method. So you do that with a sequence diagram generally corresponding to a single scenario here. All right, what are the parts of a sequence diagram? I think I just described all of that right there. Got ahead of myself. But that is what a sequence diagram is. Sequence diagrams can have conditional logic in them, like showing if this thing saved successfully or if this thing didn't save successfully. What you typically would not do with a sequence diagram, however, is show every single subflow in your use case. So having a sequence diagram that attempts to show this is the post request to the office visit endpoint. This is the put request to the office visit endpoint. This is the get request to it. This is how you create the procedures that are part of it. That is just going to create a really messy sequence diagram. Don't do it like that. That's pretty much all I have to say, is create multiple sequence diagrams if you feel so inclined. For this project, we've just been asking you to do one, just showing a single scenario here. All right. What are the parts of a state diagram? How do you draw a state diagram from a scenario? So a state diagram like you would guess from the name of it, is basically a diagram form of a finite state machine. So it shows these are the different states that our thing can be in, and what state you start in, what states you might end up in, and how you go from one state to another. So you have arrows that connect the states and say, we move from state A to state B when X happens, and oh, by the way, we also do Y as some side effect. So you've all already seen how to do state diagrams, certainly in 216, because Dr. Heckman loves finite state machines. You probably saw it in Automata. I don't think we've explicitly done state diagrams here, at least not for the projects, I think. But that is what they're used for, and that is how you use them. A natural use for state diagrams is when you have an object that can be in a whole bunch of different states, and you want to track how it moves between them. So, as an example that I used in 216 over the summer, you might have a support ticket that comes in from a user. It is initially going to be in your pending state, and then if whenever someone claims the ticket, then it moves into, or claims the ticket to work on, it might move into a claimed state, and then it goes into the working state once they actually start working on it. And then it can go into a state of waiting for user information, or waiting, or the tech is still working on it, or it can go into a state when they're done with it, have completed. And the state pattern, and thus the state diagram, is a natural use for things like this. Sir?
So are these scenarios, like in the our scenarios used when drawing sequence diagrams, are those the same as like acceptance scenarios? Do those have specific values?
So a sequence diagram, you typically don't show specific values, at least for a large system, because that's going to clutter things up quite badly. So typically the way I've done sequence diagrams is you show that we make a request with an office visit that is part of it, and then you show conditionals of if everything saved successfully, you do X, if everything didn't save successfully, you do Y. So it accounts for that we might have good data or we might have junk data, and then it shows how either is treated. Does that work?
Yeah. So
okay.
It's not the same scenario.
It's very close. So it is basically an acceptance scenario minus the specific values that are present in it. It is the same scenario if a user makes this type of request, and then you show what the system does in response to it. But it is more like a subflow through a use case than exactly a acceptance scenario. All right. What are design metrics, how are they used, and what are the characteristics of all of these different things? Design metrics are basically something that let you attach numbers to a piece of software that you are working on or have worked on to get some feel for how good it is according to a variety of different characteristics. So I'm not going to say that having all high numbers or all low numbers or all of the right ones on each thing makes your project good versus bad. But it is something that you as a smart human can use the numbers to inform you. The numbers are not the be-all and end-all, but they are still something that is helpful here. All right. Various different types of metrics here. Coupling is the extent to which you have two different entities that are basically intertwined and mangled together when they perhaps shouldn't be. So you generally want low coupling. Low coupling means that each class is mostly just working with stuff in its own class, and it's not making regular use of methods out of another one that it has no business being part of. Cohesion is the extent to which the things that are within one class are functionally related to each other. So having a class that represents a single real-world object or a single abstraction thereof or whatnot is likely to give you good cohesion here. So an example of a class that would probably have poor cohesion is if you had something that represented both a computer and a dog. There's going to be a whole bunch of things that are related to the dog, a whole bunch of things that are related to the computer. Not very good cohesion between the two of them. Encapsulation is a metric of basically how much of the stuff within a class is private. So how many of the methods are private, how many of the fields are private. In general, aside from static final things that are used as constants that you maybe want to make visible to others, pretty much all of your variables should be private. Methods, there's less of a clear answer here, because sometimes you want to have private helper methods, sometimes it's not necessary. So there's not necessarily a single great answer for that, although more private methods suggests that you're doing a good or a better job of having a simple interface that you expose to the outside world. The simpler the interface you expose, the easier it is to change your underlying implementation without breaking that interface. That being said, you can take it too far. If you have a class that has no public methods, it has a really simple interface, so you can change the underlying implementation however you want. But with no public methods, it probably doesn't do very much good either. So there is a balance that has to be struck here. So for some of these, it's desirable to have high values, like encapsulation high is generally good, cohesion high is generally good, coupling low is generally good. And we have a few other metrics that I believe are mentioned in the slides that have different preferred values as well here, and I believe some explanation thereof. Yeah, there we go. The metrics topic right here. Right. So here is a whole bunch of different other metrics we have, and again, there's different trade-offs that are involved. Number of classes, we generally want to be higher because that means we've broken things apart into smaller classes that do a better job representing just one thing. But like everything, you can take it too far. Lines of code, generally fewer lines of code is better because it means you have a simpler system. If you have fewer lines of code because you stuck your entire application in a single line, that is, I can see from the smile, yeah, you don't want to do that. That's torturing your application to meet a number here. Methods per class, lower is generally good because it means you have simpler classes which are easier to work with. Number of children and depth of the inheritance tree, generally better as low, but there are advantages to making it higher. A really tall inheritance tree means that if you change something that is closer to the root of the tree, then it is much more likely you'll break something that is in one of the subclasses, and there can be more unintended consequences that are difficult to plan around. That being said, a deep inheritance tree means that you're doing a good job reusing code, so having a deeper tree does have some benefits. Number of children, we typically want lower as well because, again, if you change something in the parent class, that gives you fewer opportunities to break something in the child class. But more children means, again, more reuse here, so that is not a bad thing. You'll notice in the iTrust2 system, everything in the persistent class extends domain object. So that is a relatively shallow but relatively wide tree. The inheritance tree is just some class extends domain object extends object. Or maybe you have ophthalmology surgery extends office visit extends domain object extends object. Not a particularly deep tree. It's not like it's 10 classes tall or something. But it does become relatively wide because we do have everything that comes from domain object here. And as said, we want generally higher hiding factors here because it means that more stuff is private and you don't have to worry as much about breaking an interface as part of changing things. All right. That looks like that is pretty much what we have for the design section. Any other questions about that? All right, good deal. So secure design. So I'm not going to go and try to rattle off all of these principles of secure design right now, but I will pull up what we have right here and then can at least talk somewhat intelligently about all of these. So IEEE is a large-ish organization within the computer science realm, and they maintain a list of design principles for designing a secure system that can aid us in coming up with a system that is secure by design and is less likely to have major flaws later on. So the first we have here is earn or give but never assume trust here. And what this means basically is that you shouldn't trust the user to do the right thing in terms of calling one of your API endpoints and then calling another one. You shouldn't assume that a user is sending you clean data. You need to make sure that there's nothing malicious here. Basically assume that anything that the user could do stupidly, that they will do stupidly. Or anything that they could be malicious about, they will be malicious about. I think probably the greater threat to most applications is truly stupid users versus malicious users, because there's a lot more stupid people out there than there are malicious ones. But we need to be able to protect against both different types of users here, and this is a good start to this. The next thing we have here is use tamper-proof authentication mechanisms. And this is basically using authentication mechanisms and actually using them properly. Something like Spring Security, like we have in iTrust 2, make sure that users must actually sign into the system. We have the pre-authorized tags on all but one class worth of the methods in the iTrust 2 system, one class because we use that for demonstrating things. But we have pre-authorized annotations which make sure that, yes, even if you guess the URL or even if you happen to steal it from someone else's web browser history, it doesn't matter because the authentication mechanisms will basically disallow you from accessing something. And it is generally better to use something that comes from a vetted and established library like this rather than trying to create your own thing. Because it's hard and you'll probably get something wrong, or at least you might get something wrong, and then you have a mess on your hands. Authorize after you authenticate basically says we first want to make sure that a user is who they say they are. We make sure that someone is Joe User. And then on every request that comes in after that, we check to make sure, is Joe User allowed to access this thing here? So we first verify that Joe is Joe, and then we check to see, well, Joe's a patient, so we'll give him access to the View My Office Visits page, but we're not going to give him access to the Document Office Visit page. So we have authorization on every incoming request, and you see that in Spring with the pre-authorized tag that we have stuck on the methods to make sure that things are fine. All right. Next one we have is strict separation right here, and this says basically separate out control flow instructions from data instructions. And what this means is that basically you shouldn't just take an arbitrary string of data from a user and then use exec or eval on it. Another example of this is actually where SQL does it sort of badly, is drop table or drop database is a series of words that means nothing to Java, but is a series of words that means an awful lot to a database engine. So the difficulty with dealing with relational databases is you might have data that is legitimate data that you actually want to have stored. Because if I'm building an application that keeps track of various different SQL keywords and then what they do, I might want to legitimately save in my database something that says drop database this has a corresponding description of it will drop the database that you specified with this name. But at the same time, drop database users, while great as an example of a keyword, is also a very dangerous thing to send to your database because it intermingles your data and control flow instructions here. So we generally want to try to separate them out so that there is not a case of executable code getting mixed in with our data, because otherwise scary things can happen. As part of this, as part of helping make sure that this works properly, you want to explicitly validate all of your data. Basically, again, assume that your user might be doing something stupid, assume that your user might be malicious, and don't just assume that, well, we had front-end checks that make sure that we're not going to have the keywords drop database in it, so the backend is fine. So we want the backend to validate that the data is okay, escape things that are otherwise going to be dangerous for the database, use prepared statements, something like that. Make sure that you know what data is coming in and you're handling it reasonably. The next thing that we have is to use cryptography correctly. This is the key point of this basically is don't try to create your own cryptography stuff, because it will be painful and something will work incorrectly. So there are a whole bunch of out-of-date cryptography algorithms that you have no business using at this point because they were secure back in the 80s, secure back in the early 90s. Computers are a lot faster than they were in the 80s. So things that were state-of-the-art and deemed secure then are no longer state-of-the-art and are no longer deemed secure. So use cryptography that is created by cryptography experts, by people who are really good at this, and use stuff that is still considered to be state-of-the-art and secure. Don't just use something you found off a Wikipedia page or off of joescoolstuff.info or something. All right, identify and handle sensitive data. This is basically making sure that you keep track of your data, then you don't lose it or corrupt it or disclose it carelessly. So encrypt stuff that you're storing in the database so that if someone happens to read what you have there, they see garbage instead of actual data. Don't have an API endpoint that provides a list of all users together with all of their hashed passwords. Don't know where you might find a system like that by chance. Yeah, just don't disclose stuff that is sensitive. Always consider your users. This is basically consider that your users are stupid. So I suspect that most of us have done technical support for our grandparents. Having done technical support for your grandparents, you probably need no further example of how people are going to misuse a computing system. Even if it's not malicious, it will be used incorrectly in every single way that you can imagine, and a whole bunch more beyond that. So consider that anything that can be done wrong will be done wrong. Understanding your attack surface is basically taking a look at how can our system be attacked, what might happen to it, what type of attacks might be made. Generally, a system that has a smaller attack surface is easier to protect against. This, again, hopefully makes sense because the larger the system is, the more dependencies that are involved, the more API endpoints you expose, the greater a chance that something will go wrong with something, and then you might have total loss of control of your application. So the less you expose, the less that can be misused or abused here. Finally, we have the principle of designing flexible systems here. And what this means basically is we want to design systems where it is easy to update and retrofit things as security policy evolves. So don't design a system where for some reason the only hashing algorithm that it ever supports is MD5. MD5 is, again, one of the ones that is no longer considered to be secure because of advances in computing power. So design a system where it is flexible enough you can replace one algorithm with another one component with another one, if problems are found or if better technology comes out. This last one in particular really is hard because it's hard to design a system around the future that you don't know about. But the fewer things you have hard-coded in your system, the more things that are in properties files, the more things where you're doing a good job adhering to an interface, makes it easier to swap one thing out for another thing here. All right. What are vulnerabilities that should be investigated? We might have this in this slide deck right here, or we might not. I don't remember. Oh yeah. So this is from the OWASP list of top vulnerabilities within web applications. So let me go pull this up, and then I will quickly run through the list that they have provided. Or I won't, maybe. All right, I'll quickly talk through the ones we have right here. Yes, as the website so helpfully tells you, this is out of date. Well, it's one we have in the slides, so it's one you guys have seen, so I'll talk about this, but regardless. So injection is basically letting, is basically where executable code gets injected in alongside data, particularly when dealing with databases or maybe JavaScript stuff. But there's stuff that gets executed and shouldn't be that is intermingled with your data here. Broken authentication mechanisms is basically you don't have a good way of authenticating the user, maintaining a session, making sure that we keep track of who the user is. It might have something where it inadvertently discloses or otherwise leaks out information about passwords or session keys or other things that could be stolen, and then you could pretend to be someone else. Cross-site scripting is basically when you have JavaScript code that gets executed that shouldn't here. So here you might have cross-site scripting attacks where injection actually occurred earlier on, and then JavaScript got saved in your database as part of an office visit, and then when a user comes back to do it later, haha, you've been attacked, and now the JavaScript gets executed, and who knows what happens. Or there might be cross-site scripting where a malicious website goes and executes a post request to a URL for your bank. If you're signed into your bank in another tab, then they are able to pretend they were you and do malicious things there. Insecure direct object references basically says that we're exposing too much information about primary keys for things to a user. So if they're able to see, well, I accessed object 113 here, let's just try and see what 112 was and maybe it'll work. So you want to not have this information get exposed to a user, because then they're able to just go poking around and go looking for things that they shouldn't have access to, particularly if there's not good authorization imposed on each one. Security misconfiguration is basically just that you configured your security wrong or used defaults you shouldn't have been using, and otherwise might have fine security libraries but are configured in an unreasonable approach here. Sensitive data exposure would be something like storing everything in plain text or only doing HTTP requests, no HTTPS. So every time you submit an office visit, anyone who's using Wireshark and listening in on the network gets access to everything right here. Missing function level access control right here. This is basically missing the pre-authorized tags that we have in the API endpoints. So those are used to make sure that, yes, you have the proper privileges to access each thing right here. And then if you miss that, then you can have any user who signed in go access the create user API endpoint, and we wouldn't want that. All right. CSRF attack takes, or it has a malicious website send some forged request to another web application, potentially using cross-site scripting here. This is why the iTrust2 system has the CSRF tokens in it. I believe I showed an example of that up in class, but it sends one of these tokens when a request goes out. Make sure that the same token must come back when the next request comes in. And if it doesn't, then it says, no, you did something wrong, and it doesn't process the request here. All right, using components with known vulnerabilities. This is a case of pretty much everything has some sort of vulnerabilities in it. Many vulnerabilities you won't know about, but some you will know about. There's lists that are published. Security professionals attempt to exploit things, and they say, oh, well, there's a problem we found, you shouldn't be using this. Then there's regularly updates that are published, so if there is a vulnerability present, it's good to go get the update here. The final one here is unvalidated redirects and forwards here. So this is basically, you might get forwarded on to a malicious site accidentally if code that contains like a document.location.href equals whatever gets executed, potentially due to a cross-site scripting attack that was performed earlier. So I don't believe that we covered all of those in class. I think we only covered 3 or 4 of them, but that is at least the top vulnerabilities list and contains things to be aware of. All right, so next thing that we have here, which is probably going to be relatively quick, is design patterns and what good are each of these. So what is the purpose, or sorry, I guess before I go into that, any questions about the security stuff we talked about? All right, good to go. So design patterns first, what is the purpose of the strategy pattern here? When do you use it? What does the class diagram look like? And how does it differ from the state pattern? All right, so the strategy pattern basically works by encapsulating an algorithm through an interface and then letting you switch implementations of that algorithm when you feel like it. So you define an interface or an abstract class that is, this is what our algorithm needs to be able to do, and then you have concrete implementations thereof, and then you can use one of these concrete implementations, choose one of them at a later date. And the reason that you might wish to do this is there are some times when different algorithms are going to perform relatively well versus relatively poorly. So if you're thinking, for example, of sorting a list of data, if you have a list that is nearly in order already, bubble sort is going to be quite efficient. By contrast, if you have a list that is nearly in order already, if you have a naive implementation of quicksort, that is actually going to be quite inefficient. If you're choosing just the first or last element to pivot on, then that is going to work badly if the list is already nearly in order. In that case, you are going to get worse runtime than you actually get with bubble sort here. So you encapsulate a sorting algorithm and define what its interface looks like, and then based on what you're the smart human, know about the data you're working with, you can then go use whichever algorithm seems reasonable at that point in time. The difference between the state pattern and the strategy pattern is that the state pattern is all about data and the strategy pattern is all about functionality. So they otherwise look relatively similar. The state pattern encapsulates the data that we're working with and lets you move from position to position within your state machine. And the strategy pattern lets you choose which algorithm you're working with. But one is data and one is actions based. The purpose of the observer pattern here, and when should you apply the pattern? The purpose of the observer pattern is it basically lets you register, or it lets you register multiple things that care about some data that might change, and then notifies whatever is being observed when that data has been changed and is ready to update. So an example that you guys might be familiar with from the recent iTrust2 project is you're adding support for adding in blood sugar diary entries. And we have 2 different ways that this data gets displayed. We have a table of data, and you might have also implemented a chart of data. Maybe you want to implement your system so that if I submit a new entry, then it is automatically going to show up in the table or the chart, and I don't have to reload the page to make it happen. So you could use the observer pattern here, where you make both the table and the chart observe the data source. Then when the source of data, the entries actually changes, then it can go notify both of the displays of it, hey, I have new data, go update yourself. And this way, both things are told about when there is something they need to care about. And they don't have to keep polling the underlying data continually. Polling the data all the time is a bad idea for all of the reasons we talked about in operating systems. So the observer pattern is a much cleaner approach for this. So basically you apply it here whenever you have some presentation, particularly multiple presentations of your data, that you want to have do stuff when the data underlying it changes here. What is the purpose of the composite pattern here, and when should you apply it? The composite pattern basically says that we are able to compose objects together into increasingly complicated structures. So rather than just having an object that has nothing but primitive fields inside of it, we're able to create an object that is a user, and then an office visit that has a user that is its patient, a user that is the HCP who ordered it, a prescription that is what the patient has been prescribed, or perhaps a list thereof, lists of diagnoses, and so on. So you can make more complicated structures out of these and continue to compose your objects together in whatever way that is necessary and seems reasonable for the domain you're working with. What is the purpose of, or then the last thing, what is the class diagram for all of these? Wikipedia has pretty good pictures of all of them as well, and it just shows you what it looks like. I would say that rather than trying to memorize what the class diagram is, understand what each of the patterns do and what you use it for, and then the class diagram is probably going to be relatively straightforward to reproduce from there. So if you understand that the strategy pattern is about having an interface or an abstract class with concrete implementations thereof, then you can think of one class with 2 or more subclasses, and then some other class that has a field that is an instance of the superclass that is the specific thing that has been encapsulated that we're swapping out later. So understand what it does, and then you can reproduce the class diagrams as necessary. All right, what is the purpose of MVC? MVC is nice for developing applications because it lets us split things up into different components so that we have our data separated from how our data gets presented, which is separated from how do we actually tie everything together. So our data is the model, it's what we care about. The view, of course, is what the user interacts with. And then the controller is responsible for taking user input, using it to update the model, taking the model, using that to update the view accordingly. How do each of these patterns fit into MVC above? The strategy pattern is something that generally works well for the controller, because the controller is all about taking actions here based off of what data we're working with. And we might take different actions based off of different data that we're dealing with. Observer most nicely fits with view right here, because the observer, or the view is observing the data right here, so whenever the data changes, you want the view to update accordingly. And model works nicely for our with the composite pattern here. So like mentioned, with the office visit having users and prescriptions and diagnoses, we can compose together multiple different classes into structures that make sense, and then this is our model, this is the data that we care about for it. All right, given a description of the above design patterns, determine which design pattern is described. I've just described them. Hopefully if you get a description like that, it then becomes relatively clear. I would like to think that you're not going to confuse things like the composite pattern versus the strategy pattern. They're relatively disparate. We're not going to have you explain more nuanced descriptions like what is the difference between the factory pattern and the abstract factory pattern and the builder pattern. That's out of the scope for what we have right here. All right. And given a design pattern from above, determine the type of it. So the types that we have here are behavioral, structural, and creational here. So going from the bottom up here, the composite pattern is a structural design pattern since it specifies how is our data structured, how are things put together. The observer pattern and actually the strategy pattern here are both behavioral patterns because they describe how does our application behave. Creational patterns are things like the builder pattern or the factory pattern or whatnot, because that is how do we actually construct objects based off of what we're trying to do here. All right, I'm going to grab another drink. I'll be back and talk about implementation of these tests. All right, any questions about the design stuff before we talk about testing? Yeah.
Could we skip ahead to stuff that was on the midterm?
Sure. Yeah. Okay, so coverage we would have already done here. So I actually don't remember exactly where the midterm fell in this. Let me look at the schedule. All right. So there's actually relatively little still on the study guide that was not stuff that has been covered at least a little bit in the midterm. Like we aren't going to have specifics. We don't have specific stuff about. We don't have specific stuff here about the accessibility things. Software process we have a little bit. Software process is after midterm, and that's mentioned. So I'll talk a bit about that. And then there was a thing on performance testing. All right. So what is an operational profile? So that is something that is used in performance testing. So an operational profile basically describes these are the types of actions that a user might make, or the types of actions that a user might perform, and ratios of relatively how common are each one. So you might say that our operational profile consists of creating new users, documenting office visits, and requesting appointments. And then we'll say that 5% of our workload is going to be creating users, and 45% of our workload is going to be requesting appointments, and 50% of it is going to be documenting office visits. So that, of course, is going to be an incomplete an incomplete operational profile for iTrust2 because there's a whole bunch more things that you can do with it. But that at least is an example, and then you can tailor your performance tests around that. So you want to make sure that your performance tests are testing things according to whatever operational profile you come up with. This profile should be well grounded in some sort of information about how users actually use the system, and then you can test according to that profile. And this way, you can perform repeated performance tests over time against the same profile and see how things are changing. All right, processes and practices. I think a bunch of this stuff is new here. Yeah. All right. So, pull request development, feature-based roles, issue trackers, continuous integration, and automated tests. So, pull requests are nice because it gives you basically a way to do quick code inspections as part of is a regular part of the process. It lets everyone see where everything is changing or what everything is changing, and different branches make it easier to isolate different things that you're working on and not step on each other's feet so much. Develop each piece of functionality in a different branch, use pull requests, review the code as part of a pull request. If you find something you object to, pull requests make it easier to see what changes have been made in response to a concern. If something goes horrifically wrong, it's relatively easy to revert an entire pull request rather than trying to revert individual changes. Feature-based roles are nice because most of us have one part of the system that we are most comfortable with or most enjoy working on. I've done enough development at this point to know that I really do not like front-end development. So a feature-based role where I was able to do exclusively or predominantly back-end stuff, I would be much happier with and I think much more productive. Some people, however, like Zach, prefer working on front-end stuff. So it lets people work on what they are comfortable with and what they most prefer doing. And by having one person who sort of owns each part of the system and makes sure that each thing is getting done properly. Issue trackers are, of course, a great thing because it lets you keep track of this is what needs to be done, these are bugs that have come up. If you manage to work on a reasonably large software engineering system and not introduce or find any bugs, I will be extremely impressed by the former and somewhat alarmed by the latter. So issue tracking is good to keep track of these so that you know what you need to do with it. CI and automated tests is what we just talked about earlier this week, so I'll skip over that. The differences in story points, ideal time, and elapsed time. Story points are a unitless thing that you use to estimate relative to each other how difficult are these different tasks. So a 3 doesn't mean that it is 3 hours, but a 3 means that this is, by our assessment, less difficult than a task that is a 5 and more difficult than a task that is a 2 here. And this is nice because it abstracts away individual developer performance of maybe you have one person who's really good and gets everything done in half the time of your average team member, even though a certain task might be more difficult for this rockstar developer than it is for other tasks that she works on. Ideal time is how long you think it is actually going to take some specific person to work on some specific task. And this is nice because ideal time lets you actually budget the time that you're spending working on a project. And it is customized for an individual developer. So I would say that my ideal time when working on back-end stuff is going to be much better than my ideal time than working on front-end stuff, just because it is technologies that I am the most comfortable with, have the most experience with, and am better at solving problems with here. So this lets me say, well, this is a 3-point task in general, but I think I can get it done in 2 hours because I'm really good with these technologies. Or this is a 3-point task in general, but I think it's going to take 6 hours because I have to go do an exploration of this technology. I'm not comfortable with it. Elapsed time is how long something actually took, because none of us, to the best of my knowledge, are actually military androids. We are all people. We all get distracted by things. So there might be other things that come up. There might be other things you have to learn along the way. So there is still time that is other time that happens as a result of that. Justifying estimates for requirements. There are wrong answers, but there are not necessarily right answers. Or rather, nearly any answer can be a right answer if it is reasonable and there's justification behind it. If you say that it is going to take 100 hours to do something, that is probably a wrong answer, unless it is a task that is so big that it needs to be broken down into 20 smaller ones. But if I say that a task is going to take 2 hours and Dr. Heckman says she thinks she can do it in an hour and a half, or she says he thinks it might be 3 hours, all of those could be right answers. We all have different levels of expertise, familiarity with things, comfort with different parts of the system, concerns that we're taking into consideration. So explaining why you think something is going to be a certain time is frankly more important than the exact value, as long as you're not off by a substantial amount. What do we do with inspections? You can inspect pretty much anything. You can inspect your requirements, you can inspect your test plan, you can inspect your design, you can inspect your implementation. You can inspect your your operational profile. Anything you want, you can inspect. Why do we do presentations? Why do we do interviews? We do presentations because we often have things that we want other people to know about. So you had to do the presentations you did 2 weeks ago in lab because you were presenting the project you were working on. You had something to demo to us. You wanted to show this is the thing that you've done. You wanted to impress us. You wanted to get points for it. You also have presentations that you do to your boss to show this is what I've been working on over the last 3 months. I'm making progress on X, Y, and Z. You might do a presentation to a new hire to show them this is how we do things around here. This is our technology stack. This is where our company resources are located. When you're doing presentations, when you're doing presentations, you have to keep in mind your audience first and foremost. If I'm doing a presentation to Dr. Heckman, I'm going to go into substantial more detail than I would if I'm doing a presentation to my mom. Of course, I want my mom to know what I'm up to, just like I want Dr. Heckman to know about it. But my mom has a sociology degree. It is admittedly a sociology PhD, so she's not stupid, but she's not going to be interested in or care about the details of the implementation like Dr. Heckman would. So take your audience into consideration so that you don't bore and don't confuse your audience. Why do we do interviews? At the end of the day, I hope that most of us want to get a job somewhere, and interviews are an essential part of this because that's how job interviews are done, basically. You have your prospective employer who wants to get a feel for multiple different candidates. They interview them. You show off what you can do. You answer your questions. And you hopefully don't look like a fool. What do you consider when you're doing a technical interview? You should be aware of the type of interview that they're going to be performing. You might get told some information about we expect you to come to a whiteboard interview, and that will probably include writing some sort of code up on a whiteboard. Implementing something to satisfy a solution they've asked for. As practice for this, it is probably a good idea to actually practice these rather than just programming in your IDE, because programming on a whiteboard is substantially more painful than it is programming even in Notepad, and substantially more painful than programming in Eclipse or Visual Studio or some reasonable piece of software designed for it. You might have an interview where it is with basically just the technical lead for the project, and they grill you with questions until you get to the point where you can't answer anything anymore, and they want to see how much do you know, and are you going to try to lie your way out of it. Don't try to lie your way out of it, because generally the interviewer knows more than you do, particularly when you're interviewing for relatively junior level positions. So you want to say, I don't know, and that's fine. So there were a couple times when I was teaching operating systems where I had a couple of my students ask me questions, and I was like, well, I think the answer is probably this, but I'll have to do some research and I'll come back to you tomorrow. That is very much like an interview there, and I give them the best answer I have and then follow up with more information when I have that extra information. You might also have panel interviews where you have multiple people who are interviewing you at the same time. These tend to be stressful because then you feel like you're being judged not on everything you get wrong, not just by one person, but by 4 people. Exciting that is. That, I think, is pretty much all of the process stuff here. All right. Why is teaming important? Well, we all work on teams with other developers. Most projects we're working on are too large for one person to feasibly do by themselves. So we do actually have to work with other people. And it's usually not other people that we actually asked to work with. So we try to put you with people that you've asked to work with in this class. But in general, when you're working in a corporate environment, you're told, this is your team, this is the project you're working on, good luck. And you don't really get to say, well, I don't like Bob, he's been mean to me, I want to work with someone else. It's, well, you're working with Bob, make the best of it. So, characteristics of a good team, you probably could answer this one for me at this point due to good teammates you've had, bad teammates that you've had. Technical competence with the material is good, but I think probably more than anything else is being responsible and communicating properly. You might have someone who's not particularly good at the material, where you might have someone who's not particularly good at some of the technical stuff you're working with, but is great at keeping track of tasks and making sure everyone knows what they're doing. I've worked on a team project with someone like that. He probably couldn't have programmed his way out of a paper bag, but he did a great job keeping track of these are the tasks that need to be done, this is what we need to accomplish to see the project through the end. And in the end, he ended up being a great teammate because he made sure that no one forgot what they were doing, even though he didn't get very much of the programming done. All right. What is privacy? Privacy is about keeping information protected, keeping information secure, not disclosing stuff, not selling your information off to the Russians. Why is it important? Many people have an expectation that we will keep their personal information protected. So this is why websites like Google and Facebook have privacy policies that they then apparently ignore anyways. This is why medical information you typically keep encrypted, just to minimize the chances that information is disclosed when it shouldn't be. What are microservices? This is what we just talked about Monday. You break the application down into smaller bits and pieces, scale each one independently, have them connect to each other through REST APIs, and this way it's easier to scale what you need, and if something goes wrong, it's easier to fix. Infrastructure management, I'm not going to talk about again because I just talked about that an hour and 45 minutes ago, and you were all here then. What are crucial conversations and when are they useful? This is basically how do you deal with substantive disagreements about something, be it a software project you're working on or personal relationships or whatnot. But you have something where there's decently high stakes involved, and you have tangible disagreements, not disagreements like I want to go to McDonald's versus I want to go to Burger King, but disagreements over what approach you're going to take for developing a project or assigning work out or responsibility for things. And the fundamental grounding for these is try to start with a mutually agreeable set of facts here. So you start by laying out the facts and trying to make sure that everyone agrees upon these, and then you can start explaining different opinions and justifying your opinions based off of the facts. But when you can't agree on even the facts that you're working with, it is very difficult to arrive at supported arguments or conclusions based off of it. So you start with that. You try to hear each person out. You don't want to tell the other person that you're dealing with, you're stupid, you never get anything right, I'm not going to take your opinion on this, we're doing it my way. Because no one likes hearing that. So it is difficult, but an important skill to be able to respectfully disagree with someone, and I think respectfully say, no, this is why what you have argued for is incorrect. So this actually came up in class I was in this morning. Someone asked a question, and the professor managed to very respectfully say, no, you're wrong about this. So he asked, is there a scenario where something could happen? And she said, hypothetically, maybe, but I would have a hard time imagining where this could actually occur. She said something to that effect. And she managed to acknowledge, yes, this is a legitimate question that you could have, but this is why I don't think that this thing could come up, and then she supported it with evidence behind it. So hear the other person out. Don't tell them they're stupid. Establish facts, and then use these facts in order to draw your conclusions from them. That, as far as the study guide, is, I believe, all that we have touched on since the midterm. There's other stuff that we have covered in some detail, like the accessibility stuff that, beyond being vaguely familiar with it, isn't fair game for the final exam. And there's a whole bunch of stuff like the team work days and whatnot where there wasn't really anything covered in class. So I believe that is it as far as what we've done. If there are any questions now, either about stuff I've talked about or stuff that was on the study guide that I skipped over, I would be happy to answer them. I'll stick around for a few more minutes so that if something occurs to you, you can ask me about it. And if there's no other questions you guys have, nothing that occurs to you, then hope you all have a nice week and a half, and I'll see you at final.